Okay, our first speaker is Jamie Kennea from Penn State, who's going to give us an intro to the Across project. Take it away.
Yeah, so my name's Jamie Kennea. You may know me from my other role, which is working on the SWIFT mission, which I will talk about in a bit, actually. But today I'm going to talk about an overview of the Astrophysics Cross-Observatory Science Support Across project. So I'm going to give an overview talk, and then Craig Pelligrino is going to give a talk immediately after me, giving some of the technical details. And I'm not going to, what we're going to do is rather than me stopping for questions, I'll just go straight to Craig, and then you can ask us both questions after we give him both of our talks. Thank you. Sorry. I need to hold the microphone. Okay. Anyway, hopefully people online just about heard that. All right, so this is an overview of the talk. I wanted to mention the Across core team at NASA Goddard Space Flight Center under the Physics of the Cosmos program. We have Brian Hemensky and Chris Roberts, who lead the project. I am at Penn State University, and I'm the project scientist on Across. Marshall Space Flight Center, we have Dan Kuczewski, Michelle Hui, Adam Goldstein, and Corey Fletcher. And Goddard Space Flight Center, we have Tom Barkley and Sam Frock, Christina Hedges, Craig Pellegrino, who you'll see in a minute, Tyler Pritchard, Kirill Voroboyev, and Sam Wyatt. And Corey Elliott on the right here is going to be joining us in October. And I wanted to, the talk here, I'm going to talk about the inspiration, some of the inspiration for Across, where I'm going to talk about Swift. Then I'm going to go into the background, the vision, the things that we're focusing on, the current status. I'm going to briefly mention the fourth TDAM workshop, and there won't be a Q&A at the end of my talk. All right, so Swift kind of forms a lot of the inspiration for how we're building Across. So launched over 20 years ago, Swift has defined how a space-based time domain mission should operate. It has open data and an open TOO policy. And, it's discovering transients as well as doing follow-up observations, and it has very, very rapid slewing. So we're observing hundreds of targets a day with Swift, and that means you can do things like observe a target every day for like a kilosecond. Importantly, Swift has an API. We've had an API, I think the first release of our Python module that allowed people to access the API was 5 years ago. And the API does the following things. It does TOO submission. We have and this includes now the ability to actually get Swift to observe something with no human in the loop, which is a first for a space mission. We have visibility calculators. You can query the observing plan, easy access to data. We've abstracted the complex kind of HESARC thing into a very simple API query, and you can get things like instrument configuration. As we're astronomers, this is we take a Python first approach. There's the pip install Swift tools if you want to install it, and we also have example Jupyter notebooks for doing this on the Penn State Swift website. So Swift has encountered a bunch of issues linked to basically being a small mission run by a skeleton crew. Like how do we coordinate with other missions, scheduling information for other telescopes is an extremely heterogeneous landscape. So, finding out what XP is looking at and what Hubble is looking at, you're going to websites, you're looking at text files, you're looking at CSV files. If you're lucky, they might have an API or they might have a VO protocol implementation, but it's extremely heterogeneous and very difficult to navigate. But also there's how do we effectively communicate with the stakeholders? That means the observatories themselves, but also the users. So these are all problems that Swift currently has that it hasn't really solved in an easy way. And I think Across is going to be attempting to solve some of those problems. Swift is going to end soon, question mark. And we've learned a lot of lessons over the last 20 years. So one of the things that 20 years into Swift I'm thinking about is how do we preserve the lessons that Swift has learned? The worst thing that would happen with Swift is that, it burns up in the atmosphere, and then everything that we did is essentially forgotten, and the next mission is just invented from scratch. So we want to be able to sort of keep those lessons and learn them and somehow formalize them. We want to be able to take those lessons and apply them to other missions. So The idea here would be to develop tools that allows any mission that NASA has to do a similar kind of operations as Swift does, but without having to reinvent everything from scratch. And yeah, and also maybe expanding those lessons to outside of NASA as well, if we could teach any of you guys anything. I'd say the Swift TOO API has been wildly successful. We've had over 30 million API requests in the 5 years it's been running. And it's also allowed third parties to build Swift response into their systems. So like the Tom Toolkit and also Sky Portal have the ability to submit TOO requests for Swift built into them by using our API. And but the question is, how do we generalize these tools for Swift and apply them to all NASA missions and beyond? So now to talk about Across. Across is a response to the US National Academy's Astro 2020 Decadal Report, where they recommended that NASA focus on TDAM science. NASA's PCOS was asked to conduct a study investigating ways to improve coordination within the NASA fleet, and the US ground-based observatories and internationally eventually. And the recommendation, we were going to recommend implementation options for enabling TDAM science. So out of this came the Across pilot, which is the concept is to enable a whole of fleet approach to TDAM by providing organizational workforce and technical infrastructure, and involving NASA's operating missions and those in development. And we want to enrich and support the broader TDAM ecosystem. And the QR code here links to a paper that was published on the concept behind Across in Frontiers of Astronomy and Space Sciences. So here's the vision statement, or a mission statement for Across: to provide NASA's fleet-wide coordination infrastructure and enrich the global TDAM ecosystem, and partner with missions, observers, and science teams across multiple astrophysics domains to maximize the science return of NASA's contribution to the evolving TDAM ecosystem. So what does this mean? Well, we kind of taken a four-pronged approach here. We want to develop science feasibility tools. We want to provide modern TOO resources, a TDAM web portal, and community engagement and innovation program. So apologize, there's a lot of words on these pages, but I'll just try to summarize it. So science feasibility tools, we want to develop essentially a homogeneous way of accessing short and long-term observing plans for all missions. And we want to be able to provide target visibility and observability, and constraints on planning and scheduling feasibilities, and mission target histories. So, as I said, for Swift, we always had this problem where finding out what other missions were doing was extremely hard. So the idea of Across is to centralize that data and make it in a homogeneous way that means that there's a one-stop place where you can find out everything you need to know, and it's presented in a standardized API format. We want to add value-added applications for wild-field instruments. So, if a GRB goes off, was it in the field of view of like 20 different telescopes? Things like GW events, like what's the probability enclosed within the LAT field of view for a GW event? Those kind of tools. And for ground observatories, we want to have analogous capabilities, as we're saying, for space here. So ground-based observatories are built into our system. We want to modernize TOO capabilities. Swift TOO API has been extremely successful, as I said. So we want to build an open source TOO toolkit that allows missions of any scale, from CubeSats up to like Roman, for example, to build a TOO page and API using standardized tools. So we don't want people to reinvent the wheel from scratch every time. We want to just provide them with either the open source tools to do it themselves, or we could host a TOO page for them. And one of the first things we're going to do is host a TOO page for the upcoming Pandora mission, which is a pioneer. It's like a $30 million mission, very small. They can't really afford to do it themselves, but we're going to do it for them. And this is going to be there's going to be both an API and a web application. TDAM web portal, we're essentially building a website that will have resources for doing TDAM observations, all the information about all the missions that NASA has that can do TDAM science, and links and references that allow people to go to our website and then jump off to where they need to go to next. There's going to be dynamic content. So our API tools that we're building will have front ends on this website that will allow people to look at, to visualize things like target visibility and what targets are being observed and everything. And we're going to have a help desk. So the idea is that you can have subject matter experts helping you do your coordination. So when the next big event occurs, and you don't know how to coordinate different observatories, you can come to us and we will aid you in doing that. And everything we're doing, thanks. Everything we're doing is open source. It's going to be hosted on GitHub, and we hope to have this all released soon. There are red tape issues within NASA of doing that. And the community engagement, well, we're organizing TDAM workshops. We're about to have the 4th TDAM workshop, which I'll mention in a minute. But we also want to have tutorials and training on the Across tools and try to facilitate communication between observatories. In the future, we may have funding opportunities. Obviously, with the current situation, all funding is a little bit up in the air, but the original plan was to have a AO call that allowed people to obtain funds to develop tools that are well aligned with Across. So this would be like for software, and in the future, maybe other things could be proposed. This is all TBD right now, of course. We'll know where we stand a lot more clearly in the next fiscal year. And Across wants to participate in external community-led initiatives. So here I am, basically. I'm doing that right now. All right, so the current status, we've implemented an agile software development process in GitHub. We have on staff both professional programmers and scientific programmers. So we have people who know how to program in TypeScript, which I don't. And we also know people who have scientists who are programmers as well, like Craig and Sam Wyatt. I have to say, finding good programmers who are good scientists, they're kind of unicorns. So we're very, very lucky to have Sam and Craig. And also our programmers are helping us build this system in a way which is scalable and hopefully will be long-term maintainable. And the idea is that NASA will continue to fund this for a long term. So we're currently working through the red tape on the open source release, and we're hoping, or we're anticipating, that all of this will be launched at the time of the 4th TDAM workshop in October. So about the 4th TDAM workshop, the registration is still open for this, I believe, at least until today, I think. Is it? Sorry? 27th? Well, yeah, sorry, 3 days' time. So you're still welcome to register for this if you haven't already. The theme of the meeting will be community-defined, coordinated observing concepts for rare and important transient events. So the idea here is to kind of discuss about how we want to react as a community to the next 170817 or boat, something that happens every, like, you know, however many years. The things that are really hard to propose time for, because often, you know, you're saying, I want to do this thing, but it's only going to happen once every 10 years. We've been talking to observatories and community members about how we can best kind of unite together and maybe have a large coordinated effort which is centrally organized. But I know there are a lot of people who won't like that. And that's why we're having this meeting, is so that everybody gets together in a room and decides how we want to do it. So anyway, so that's the introduction to Across. I wanted to quickly talk about something else, which came up in the last few hours. So I said that Swift is possibly going to end soon. And this afternoon, NASA announced that they are going to attempt a Swift boost mission. So there will be a satellite or an orbiter which will be launched and will grab Swift and attempt to push it up to 600 kilometers and extend the lifetime of Swift maybe another 20 years. And this is the NASA release that came out at 1 p.m. today. There's a link on the bottom. And here's the company that's going to do it is a company called Catalyst Space. And on their website, they have a few images kind of showing the concept here. So you can see that this is free-flying mission that with solar panels that will attach to the bottom of Swift and will basically rocket propel us to a higher orbit. So that's pretty exciting. And yeah, that's it from me. So I'm going to go. Sorry, Karen.
Thanks, Jamie. This is super exciting. Jamie will not be taking any questions.
Not right
So,
now.
save all of your questions, and Craig can get set up here.
Yeah,
okay,
looks fun.
Great, thank you. The next speaker is Craig Pelligrino from NASA Goddard. He's going to give even more details about the Across project. Take it away.
Okay, great, thanks. Yeah, thank you to the organizers for having me here. It's always great to be back in Santa Barbara, and I've really enjoyed my time here. Yeah, my name is Craig Pelligrino. I'm a support scientist at NASA Goddard. Like Jamie said, I'm working on the Across project as well. So I'm going to give a sort of overview of our tech stack and our sort of system implementation and architecture. Okay, so Jamie gave a really good overview and background of Across, so I'm going to keep this pretty brief. But again, just to reiterate, Across is sort of NASA's response to the decadal recommendation to invest heavily in TDAM science. So our goal is really to increase the operational efficiency of NASA's observatory fleet in order to better enable TDAM science. And as a result, we're also hoping to sort of passively enable or improve other science cases as well. So we're doing this by what we call improving science situational awareness, or SSA. So that involves things that Jamie mentioned briefly that I'll talk about a little bit more today. Things like centralizing observing schedules in a homogeneous format to be accessible, both planned, scheduled, and performed schedules. Things like building observing tools for astronomers and observatory staff, such as joint visibility calculators, integration or exposure time calculators, et cetera. And things like developing TO management systems that will tie into existing and future NASA missions, as well as community resources like TOM toolkits, for example. And so I really want to emphasize that this is for the benefit of both astronomers and observatory staff. So for astronomers, I know a common question that I've had, and I'm sure many of you have had, is if you know that some mission or observatory is observing this target, how can you best schedule your own complementary follow-up of that interesting event? And also what telescope resources have or will be observing some interesting target. And then for observatory operations staff, we're really trying to provide a sort of centralized location for y'all to host things like observation schedules. We can manage TOO submission forms or provide that as a tool for you so you don't have to like build your own custom TOO submission, things like that. Okay, so for our version 1 launch or capabilities, which we're planning to have sort of released in the late October to coincide with the 4th TDAM workshop, we have basically 2 main scientific capabilities that we're hoping to have. The first is this multi-facility observation schedules and status information. So mostly planned schedules of what NASA facilities are planning to observe, as well as coincident visibility tools across different NASA missions to find sort of joint visibility windows for astronomers or NASA folks to schedule observations. And we're going to be doing all of this through public-facing architecture, such as front ends and APIs, which I'll talk about a little bit more. And then for our version 2, which will extend from late October into the near future funding provided, I guess, we're hoping to expand our support and our infrastructure to enable ground-based observatories as well. We're trying to build out our TOO management system, and like Jamie said, we're going to use Pandora as sort of this test case to do so, and also build out our TDAM toolkit, which is a sort of community library of tools that will facilitate TDAM science using Across data products. Okay, so here's a plot or a figure showing our system architecture. So I'll kind of go through this step by step here. So our backend, we have a Postgres backend. Our server is a Fast API server. Fast API is a Python library to handle API endpoints and API development. We have a data ingestion layer, which is also written in Fast API, and this is what is pulling things like observatory schedules from NASA observatories, as well as things like TLEs from SpaceTrack to enable visibility calculations. We have an SDK, a software development toolkit, or a client, which is basically a Python wrapper around our API that allows users to, in Python, access our API, submit, get, and post requests and things like that. We also have a tools library, which is basically a Python library that has a lot of our tooling dependencies for what we need to do in our system. So things like joint visibility calculations, things like bandpass information converting from wavelength to energy to frequency, et cetera. And then our front end, Jamie mentioned this a little bit. We have kind of a complicated front end, I guess. We have a sort of static content front end, which is at this domain science.data.nasa.gov. This is static content and it's managed by NASA, and there's sort of restrictions on what we can and can't include there. So we're also building our own custom front end, which is in Svelte. And this will have things like links to our APIs, plots and tables for visibility calculations, observatory schedules, things like that. And then finally, all of this, all the infrastructure here is written in OpenTofu infrastructure as code. It's on AWS and deployed with GitHub CI/CD pipelines. Don't ask me too much about that. So the main takeaway I want to leave you with here is that we have multiple tools and multiple levels to interact with our data system. The API, the front end, the client, Python library. So there are different ways of interacting with our system depending on your level of experience with Python and APIs and things like that. So to talk a little bit about the server and the API design a bit, we use OpenAPI, which is sort of this industry standard way to create machine and human readable API endpoints. So this plot over here on the left is showing the Swagger UI interface that shows our API endpoints. So for example, this one is our get schedule endpoint to retrieve schedule information. So you can, for example, with the schedule endpoint, users provide inputs such as date range, status, if it's a planned schedule versus a performed schedule, things like that to filter out information. And all of this is also available in a sort of a JSON format here, so you can get a good sense of what the inputs are and what will be returned to you from this endpoint. This is all written using Pydantic models, which I think Austin talked about a little bit yesterday, but this does a lot of the validation and everything at runtime. So that provides a lot of stability to our endpoints. And most of our get endpoints are accessible by everyone besides things like user information. So all of the schedule information, observatory information, things like that will be publicly accessible. The post endpoints will require credentials or authentication in order to post things like observatory schedules because we don't want bogus data coming in. But I'll talk a little bit more about permissions in a bit. So our ingestion layer, like I mentioned, this is also a fast API server, and we've written tasks to basically retrieve data from all of the NASA missions which we currently support, which are most of the major high-energy astrophysics missions. And we run these on a set interval with cron tasks, depending on how often they're updated. So some of this is easy to do. Things like Swift, like Jamie mentioned, has nice publicly accessible APIs and Python libraries to do a lot of this aggregating. In other cases, this is really difficult to do. So even things like flagship missions like Hubble, this is, for example, a planned Hubble schedule that they post online. If you look closely at this, you'll notice that none of these targets have coordinate information. And so it makes retrieving all of the sort of observatory or observation parameters that we need really, really difficult. But the key thing here is that we're trying to do all of the heavy lifting so that astronomers don't have to do it. We're trying to aggregate as much information about these planned schedules into sort of homogeneous format and make it publicly accessible so you don't have to do this disgusting web scraping like we're doing. So here's a little a screenshot showing our custom front end. So Jamie in his talk showed some of the sort of static content on our site. This is the one that we're writing ourselves in-house. This is just sort of the splash page, but you can see that there are links to do things like see our data, view the schedules, browse observations, explore the API documentation that I showed a little bit before, log in the top right. A lot of the front end hasn't been developed yet. It's still a work in progress. So unfortunately, I'm just going to show sort of schematics, but we're hoping to have this done by late October. But to sort of query, schedule, and observation information, we'll have a front end page that has a table with different inputs that users can use to filter out that information. So all of the things that astronomers like to filter on, such as cone searches, date range information, bandpass information, etc. And this is really to answer the question of what has every telescope observed and what are they planning to observe in some given time range. We also have a status ingestion page, which shows the status of all of our ingestion tasks. It's easily accessible, and the point is trying to provide all this information that's easy to see at a glance. So for example, all of the telescopes that we're ingesting data for have one of these sort of card divs or whatever in HTML that show things like how often the ingestion task is run, the schedule cadence, when the next one will run and when the last one is run. And based on the information, we'll mark it as if it's active, if the task is lagging, or if it's offline. Here's a little table showing the current status or the progress of our implementation of all these different ingestion tasks. And this is actually a little bit out of date because we've onboarded a few, like NuSTAR, I think, that aren't shown on here yet. But basically, we're on track to have planned schedule ingestions for all of the major NASA high-energy astrophysics missions by our version 1 launch. And I want to especially mention that we are incorporating XMM Newton and Rubin right now in order to sort of build out our capabilities and infrastructure to include both international partners as well as ground-based facilities. Like Jamie mentioned, we'll have a page on our front end for observatory visibility calculators. We'll have the ability to find visibility windows for a given observatory as well as joint visibility windows across different observatories. So I'll show the front end here. This is just a little schematic of the front end again. But we're calculating visibility based on things like sun angle constraints, Earth limb constraints, when a spacecraft is in the South Atlantic anomaly, things like that. And we're also incorporating ground-based constraints like altitude azimuth, how far you can point your telescope in a given direction, and things like that. And this is in order to enable things like, can you schedule observations across multiple observatories at a given time? So for example, things like if you wanted to get both soft and hard X-ray observations at the same time with things like Chandra plus NuSTAR, are there windows where both instruments can observe a given target? Here's what that looks like in our API. We'll have an endpoint to get visibility windows. So again, users can input things like the coordinates, the date ranges, et cetera. And then this will return a JSON, which has information like the windows, when that window begins and ends, and the sort of constraints that are violated that lead to that being started or stopped, I guess. Okay, on our front end, we also have a user management system, which we've sort of customized and written in-house. Basically, users can register and log in through an email, and then you'll get emailed a login link. Once you're logged in, we have permissions which are set on the sort of user group level. So users can be added to groups, and then once you're in that group, you can be assigned a role. So for example, someone can have like the schedule write role so that they're able to push information about that observatory's schedules to our system. Okay, and the last couple things I want to talk about are our different Python libraries. So for example, we have a tools library, which I mentioned before. This is a library to manipulate a lot of the science products in our system. So do things like this example showing right here. Find a footprint for an instrument, in this case NIRCam, project it at a set of coordinates, and then visualize that. And this will enable things like finding coincident visibility or coincident observations between different instruments. And for our client library, this will again wrap our SDK and allow users to access our API through an instantiable client, which this example shows. You just import our library, instantiate the client class, and then you can do things like perform a get many on observatories and print out all of the observatories that we have in our system. And I should mention that we are just starting to build out all of these features right now. And I think the possibilities are really endless. So if anyone has ideas for features that you really want to see, please let me know, because we definitely want to take that into consideration. Okay, so finally, I'll just leave this up here. So for future work, like Jamie said, we're trying to continue building out our TDM observing tools. So things like the footprint projection, which I showed, and overlap to find coincident observations. Integrate more with science and mission operations centers so that instead of us scraping web pages, we have more of a balance where people are pushing their observation schedules to us. I think important for this crowd, we want to onboard ground-based observatories as much as possible to incorporate you all into our system. Support things like notifications for when new users join your groups, when schedules are posted for observatories that you care about, if there's a target of interest that's been observed lately, et cetera. Build out our TOO toolkit. And like Jamie said, we're hosting this 4th TDAM workshop, which is supposed to be developing community-led ground and space coordinated observations. We are launching our public-facing software at this 4th TDAM workshop, and we'll be giving tutorials, demos, taking feedback at that time. And yeah, use this QR code if you want to register or if you need any information about the workshop. And yeah, I think Jamie and I are happy to take questions now. Thanks.
Great, thanks, Craig. Any questions for Craig or Jamie?
Hi, thanks very much for 2 great talks. So yeah, say there is a space-based observatory that may or may not be called NuSTAR that wants to help out with the ingestion of schedules and whatnot. Sort of what's the process going to look like there, do you think?
Yeah, so I think the main thing is just getting your data into the format that we accept. And so a lot of that is available through the sort of API documentation that I showed, like that Swagger UI documentation. That is all live. The data hasn't started flowing into our live production server yet, but the actual documentation is live, and I can point you to that. But yeah, it's basically just, yeah, aggregating that information.
I think we're providing an API client which will make interaction with our system easy. So if you're comfortable using Python and comfortable figuring out how to sort of translate what you have into what we want, then it should be pretty trivial to do. I will say that the data structures that we've defined, one thing that neither of us mentioned here is VO. Andy got a question about VO when he was talking yesterday, so I'm going to address it before somebody asks us the question. The structures that we've defined for observations essentially have enough information in them that we can actually create VO protocol formatted data as well. And one of the future things we'll do is to support those. We won't at 1.0, but we will do in the future.
So this is Curtis McCulley. I'm at LCO. So we kind of came at the problem in a similar way, but we kind of came from the ground side and say building heroic, whereas you guys started from the space side. How do you see us being able to work together? Like, what can we do that we don't both reinvent the wheel?
Yeah, so reinventing the wheel is kind of is definitely something we don't want to do. But I will say that when we developed our data structures, as say they were kind of, we took the VO data structures as a starting point, because no matter what you want to think about VO, they did put a lot of thought into what they did. So we hope that the way that we've designed this would make it easy for both ground-based telescopes and space-based telescopes to be in the same system. In terms of 2 systems doing something very similar, I don't see that as a problem. What I see that is as things that can talk to each other with an API. So, if we're providing information about all the NASA missions, and because we have NASA headquarters behind us, kind of like looming over us and saying, hey, you NASA missions, maybe you should work with these guys. You can pull the data from our system and put it into heroic, right? So 2-way communication. The one thing that NASA gives us here, fingers crossed, is a stable funding source to continue this long term. I see these things being a parallel development. But what we found in the past is there's been lots of attempts to do things like this, but they all kind of fall by the wayside because the funding goes away. The hero developer moves on in their life and abandons the project. We want this to be a long-term thing, and we see ourselves as part of a broader ecosystem and not really competing with people, but sharing and kind of contributing to each other.
I think we can do one more question.
Oh, I had 2, so I better choose one then. So this is amazing news about Swift then. is that all it needs, is to be launched into a higher orbit?
That's all they're going to do.
Does the instrument and telescope, will it survive? I mean, is its lifetime?
Swift doesn't have any consumables, right? It just runs on solar power. So the only consumable really is the lifetime of the hardware and the the altitude of the telescope. So the altitude of the telescope is very much going down right now. I think the prediction is that 50% chance that we will re-enter by the end of next year. So without this, Swift is going to be done. Like, I think within the next 2 years, guaranteed it's going to be done. So yeah, but it's a very simple thing. It's just pushing us up. It's not doing anything else. It's not a servicing mission. It is purely a boost mission, and it's very cheap. It's like, I mean, cheap. It's $30 million basically.
We have time.
Hi, Sahana Kumar from University of Virginia. I have a little bit more of like a specific science case question about potential future uses for ACROSS and how it'll work with ground-based observatories. And to my understanding, some of these space observatories don't immediately downlink to here on Earth. Sometimes there's a delay in getting data from space-based observatories. So for those of us that are interested in rapidly evolving transients or trying to catch new transients early, is that something that you guys are thinking about, the time delay of getting that information from space telescopes when we're kind of at the point where we can get an observation and figure out what it is immediately from the ground?
Yeah, I think that's something that neither Jamie and I mentioned, but it's something that we've thought about, I think. Yeah, so right now we're just sort of considering the schedules, I guess, rather than the actual data products and the data availability. But I think that's something that we have at least considered building out a feature for in the future. It gets a little bit more complicated because like the schedule information is already very hard to come by, and I think the data product information might be more so. But there's also, I don't know, databases or things like MAST to do the query. So maybe it won't be. I don't know if it does.
Yeah, I mean, we have to be careful as a NASA project as to whose toes we're stepping on. So data is kind of is the purview of archives. So we won't be stepping on their toes by becoming an archive, right? But that said, some NASA missions have the concept of quick look data, which is data that's kind of available ASAP, but before it gets into the archive. And I could see us having a role there. If we were to take, like Swift has, the API for Swift has this kind of easy abstracted version that allows you to get data from both the archive and the quick look system, for example. And for ACROSS, we might consider implementing something similar to that, but more generically across all missions. I think future NASA missions will probably have more quick look data. NuSTAR has quick look data. They didn't at launch, right? Yeah, you do now. So this is a concept which more and more missions are kind of bringing online. So I think we want to support it.
Okay, let's thank both our speakers. Okay, our next speaker is Hannah Earnshaw. Please take it away from Caltech, talking about NuSTAR.
Great, thank you very much. So hi everyone, my name is Hannah Earnshaw, pronouns they, them. I am the project scientist for NuSTAR. And I'm going to be giving a bit of a mission overview, a look at our kind of evolving time domain response. And you can kind of also consider it a bit of a case study for the kind of mission that hopes to then be involved in ACROSS. So great. So yeah, this is NuSTAR. It's a NASA Small Explorer mission. It was launched in June 2012. PI is Fiona Harrison at Caltech, and Caltech is where we have our science operations. Carl Forster is the science operations manager. We have our mission operations up at UCB, at the Space Sciences Laboratory. And it had a 2-year prime mission, followed by now over 11 years as a guest observer facility. That's what we spend the vast majority of our time doing. And incidentally, our Cycle 12 proposals are due at the end of January next year, if you would like some data for yourself. So this is what the observatory looks like. There's an optics bench, where we have the grazing incident optics. There's a focal plane bench 10 meters away, and they're joined together by this 10-meter long mast. And it needs to be that length because we're focusing high energy X-rays, and that is pretty difficult. And as you see, I have a little bit of information about the telescope itself. We're dealing with an arc-minute size PSF, a 12 by 12 arc-minute field of view, so we're in a very different kind of landscape than, say, Rubin. But that is pretty good for high-energy X-rays. So I just added this very briefly last night because we had a lot of ground-based observatories. I wanted to just sort of highlight a few things that space-based observatories have to think about that are a little bit different. So we don't care about air mass, but NuSTAR, for example, it's in low Earth orbit, so we have Earth occultation coming around every 90 minutes. The actual real-time length of our exposures are sort of about twice as long as the amount of exposure time would actually get on object. We need to avoid the sun and the moon. Actually, NuSTAR can look directly at the sun, but in general, there are sort of certain angles to the sun that we can't observe in. And solar aspect angle also plays a role in terms of the thermal constraints that kind of evolve over time. NuSTAR has multi-layer insulation, which has a few tears in it, so there are certain angles which we don't want to spend too long at because it causes heating in our optics. And so that's the sort of thing where new kind of constraints sort of develop over time as there are micrometeorite hits or other little events that happen to our telescope, which we obviously can't go and fix. We just have to deal with. And then there's also ground station contact, so we can't be in immediate communication with our telescope all the time. We have to wait for, in NuSTAR's case, for pre-scheduled ground station contacts. We can schedule some more for data dumps in our case, but in general, if we want to send new instructions to our spacecraft, we have to await an opportunity there. So I just wanted to kind of quickly highlight the kind of science that NuSTAR was originally designed for. Anything from measuring the spins of black holes to mapping radioactive elements and supernova remnants, uncovering highly obscured active galactic nuclei, and yes, indeed, looking at solar nanoflares on the sun. A lot of this was kind of static science or not necessarily the kind of TOO-driven landscape that we have today. And so over time, sort of the use of NuSTAR has evolved. And nowadays, we do a lot more time domain astrophysics. So anything from the rapid response to nearby supernovae, kind of getting high energy X-ray spectra in the sort of the first few days of that, follow-up of F-bots, jetted tidal disruption events, interesting, exciting gamma ray bursts. That's actually a Swift image there, but it was very cool. Things like the boat and this repeating one that happened pretty recently. And we do a lot of sort of tracking the evolution of X-ray binary outbursts as well. And today, over 70% of NuSTAR observations are time constrained in some way, whether that is target of opportunity observations, phase constrained observations, or coordinations with other facilities. Now, I'm going to dive into that last point a bit more because NuSTAR, being a high energy X-ray mission, kind of probes a unique part of the rather wide X-ray band. So the majority of the X-ray fleet operates sort of between, say, 0.3 and 10 keV. NuSTAR probes energies from sort of 3 to about 80 keV. And so, and it's really the only game in town when you want sensitive imaging coverage in that band. And so there's this vital complementarity to the rest of the X-ray fleet that NuSTAR provides, which means it is in pretty high demand when it comes to coordinated observations. Over 50% of NuSTAR observations are coordinated with other facilities through kind of formal arrangements. And so there we have joint program agreements with various other missions, which mean that in our in the observing time that we are able to award through our calls for proposals, we also offer some of that time to other missions for their calls for proposals, and they're usually symmetric agreements, so they will also offer time to us, so that we avoid this kind of double jeopardy problem, and a proposer can propose for joint time on multiple missions at the same time. And so we've got some formal agreements with the missions here, CRISM hopefully this year, if we can kind of work out the bureaucratic aspects of that. And then also, that's kind of what NuSTAR actively responds to. Then also we then send our schedule to Swift that will usually kind of pick up the observations, which we don't have coordinations with other observatories. And so we just get a lot of broadband X-ray coverage that way. So that is a very cool thing as well. So going back to sort of time domain response with NuSTAR. So when NuSTAR was originally created, the assumption was that we do sort of 1 to 2 TOO observations every year. That is not what we do today. Today, NuSTAR averages around about 1 TOO observation a week. Over 25% of our observations are TOOs, and that's a mix of pre-approved guest observer programs and also directors' discretionary time. And it is in high demand. We increased our TOO time allocation this past year, and our oversubscription only went up somehow. So loads of people want to do time domain science with NuSTAR. And our typical TOO response time is around about a week. So our scheduling process is such that we'll make a schedule at the beginning of the week. If a TOO comes in, we can sometimes sort of upload a second version of that schedule with the TOO observation kind of replacing something in there by the end of the week. And so, you know, generally we can do a sort of turnaround of a few days. We reserve a sort of a more rapid 48-hour turnaround for these pre-approved guest observer programs that have been through ATTAC, that we know we are definitely sure it's good science and it's been peer reviewed. But we did want to do better. So in the senior review in 2022, it identified a need for enhanced time domain capabilities. And so I'll talk a bit more about that soon. But also I wanted to talk about how the X-ray time domain landscape is changing. The time domain workhorses, Swift and NICER, we're potentially going to be losing soon. If Swift gets a boost, that is great. We really hope so. It would also be great if whatever has happened to NICER gets fixed, although the lifetime of NICER is the lifetime of the International Space Station, so that's not got that long left. And so if we lose those missions, you know, other X-ray missions are going to have to sort of take up some of that monitoring slack to various degrees of success. It's not necessarily what NuSTAR was designed for. But people will want that kind of science done. And there's also just an increasing number of transients that we're receiving alerts for. So a big one is the Einstein probe, for example. We've received a lot of DDT requests for follow-up of those transients as well. And I'm sure as kind of Ruben spins up more, then we'll start getting requests from that as well. So our kind of big project over the past year or so has been improving our response time to guest observer TOO programs that require a rapid response, trying to go from this sort of less than 48-hour best effort response to under 24-hour and sort of more like a 6-hour kind of response time. So sort of originally what a TOO scheduling process would look like is that the PI would make a request using the TOO web form. It's automatically approved if it's a GEO program, but a human still needs to kind of notice it and sit down and manually rearrange the schedule to make that work, to generate the command sequence, send it over to the mock, and then an operator had to drive into the mock to actually upload it to the spacecraft. And so basically we automated just about all the different steps in this process, such that when the PI makes a request using the TO web form, if they have a pre-approved program that allows for a rapid response, they've been given an authorization code that they can use in that form. And that form then gets automatically ingested into a scheduling system, which automatically generates a schedule. It's a very simple schedule. It just basically says at the next opportunity, we salute to the TOO target and kind of forget everything else that the telescope is doing. But it can do that automatically. It generates a command sequence, it delivers and validates it, and uploads it to the spacecraft on the next contact, all automatically. And then it alerts the SOC and MOC that this request has been received and the schedule changed. And so then the SOC kind of scrambles to kind of regenerate the rest of the week's schedule and then upload that manually afterwards. We have enough time to do that because sort of the minimum exposure time in real time of a NuSTAR observation is about 12 hours. So we can do that. We had loftier ambitions originally to kind of completely revamp our scheduling system and make it a lot more automated for like to be able to generate a week's schedule, but we ultimately didn't have the software development resources for that. Anyway, we expect to go live with that system, if not this week, then incredibly soon. So that's exciting. And just before I finish off, I wanted to give a bit of a shout out to ICHEC, which is the International Astronomical Consortium for High Energy Calibration. So this is basically, it's been going for a couple of decades now. It's representatives from all of the different high energy space missions getting together in a room to talk about calibration and sort of cross-calibrate all the different instruments. It's very challenging at high energies. But in particular, as of this year, we have a new working group dedicated specifically for science operations, which I co-chair with Felix Mika First. So we'll be looking at topics like dealing with evolving orbits, scheduling strategies, how we deal with sort of system failures and that kind of thing. And I imagine we're going to be talking a lot about about sort of the various tools that are available. So yeah, if you have something that you think should be brought to the attention of the sort of high energy mission operations people, then let us know. This is probably a good forum in which to talk about that. So yeah, I will basically leave it there with just a bit of a summary on how NuSTAR is doing and take any questions. Thank you.
Thank you, Hannah. Any questions?
I covered everything.
Yeah, very far outside of my expertise. Did you have a question? No. So how do you see, you're having many more TOOs than expected. Does that have like an adverse impact on your operations, or is it just you didn't expect to have that, but it's actually fine because none of this stuff that you're interrupting was time sensitive? Do people have feelings about that?
Sure, there are feelings, especially from the people doing the scheduling. No, we've kind of had to adapt our approach to the volume of TOOs that come in. So the sort of way we do it nowadays is that when we put together a week's schedule, we'll usually put in 1 or 2 low priority targets so that there are, obvious slots that we can replace something with a TOO as it comes in, and that usually kind of gives us enough wiggle room to handle TOOs as they come in. Generally, sort of guest observer TOOs take the highest priority. So if it's a pre-approved program, they will just interrupt pretty much anything that we're doing. For DDT requests, then it just sort of depends on what else we're doing that week. Are there very complex coordinations going on? Are there already TOOs in the schedule that take precedence, that kind of thing? So it's all sort of just seeing what we're able to do.
Yeah, I'm asking because I'm thinking about, for example, HST, which I'm more familiar with. It seems very hard for them to do a large number of TOOs, right? Where it's very disruptive to the schedule. And I'm wondering, from your presentation, it didn't seem like it was that way for you. I don't know if these observatories, you talk to each other about lessons learned about, scheduling lots of TOOs. I think that would be a great idea. I don't know if it's happening.
Yeah, well, I mean, hopefully, this sort of happens on an informal basis, but hopefully we can have more in-depth discussions in this kind of new science operations working group as well, where we talk about that.
Automated rapid TOO response. How rapid and how automated? Yeah, so once the PI submits a request, then from that web form submission to ATS upload to the spacecraft is all automated, and that basically gets us onto the TOO target as soon as possible. So it sort of depends on when that request is submitted in relation to the next ground station contact, as to whether it takes 6 hours or like the best we've managed. And this wasn't even with a rapid response system. This was just a lot of good luck in terms of timing, but we got onto a target within about an hour of a trigger once. We're probably never going to get that good again, but we can brag about that at least. Yeah, generally, if about 6 hours is probably going to be a sort of the average time for that. And then we still have to sort of manually recover the schedule afterwards, but there's enough time to do that.
Any last questions?
Thank you for a great presentation. You mentioned partnering with the Across team to provide the similar sort of API-driven observation request portal. Can you talk to us about the timeline for that?
Yeah, I don't know. It sort of depends on once Across is launched and sort of how simple it is to sort of sit down and kind of generate the products that Across needs for their ingest system. I can't imagine it would take that long. It just sort of depends on of all the different things that we're doing in the Science Operations Center, who has the time to kind of get onto that. But hopefully soon.
So
yeah.
I just wanted to add something. The NuSTAR team actually worked with us very early on with Across to actually kind of prototype this concept. And we had them delivering the information we wanted into our system, and it worked very well. And I think we're very, very grateful for that exposure. What then happened with us is, of course, that we find ourselves having to go deep into development and kind of reassessing everything we've done. So what was originally a prototype was, of course, abandoned to make something more professional. And I think once we get past this hurdle, the next the TDAM meeting, we can restart that again once we have the tools that are public.
Yeah, and then with that prototype, sort of we just incorporated it into our weekly planning process, which is like once we have the short range schedule for the week, then we uploaded it to Across via their API. So it's just a case of sitting down and going, okay, how does this work with the latest version of that system? Change it up and away we go. And then hopefully, because with the TOO request at the moment, it's just a web form. We can start exploring like whether we can then have an API TO request thing with Across as well. That might make things easier.
That brings us to the end of our scheduled programming. Let's thank Hannah again.
And thanks all our speakers today and Griffin for moderating the discussion. Before you all go, just a couple of quick announcements. One is we will be starting back here tomorrow, same time, so about 8:55, just for logistics, and then we'll get started on time. And the last thing, for those of you who are staying on for our planetarium show, it has to start promptly at 5:30. So if I could ask you to be there 5 minutes early, just so we can get seated and get the show underway, so that the planetarium staff can keep to their own schedule. Thank you very much. Oh, question? It's like 20 feet in that direction. Not far to go. Okay, thanks everybody, and see you tomorrow.